Mm. Let's discuss the problem of count arrays from CodeChef Starters 120. So you are given, say, let's suppose you have an array B consisting of m non-negative integers. So let's say B is called good if you can make all the elements of B equal to 0 by performing the following operation, possibly 0 or any number of times. So uh, the operation goes as follows. Select two indexes I and j where I is less than j and let x is equal to bi or of bj. So x is the bitwise or of both these elements. And right now we need to replace bi with x minus bi and bj with x minus bj. So let's say with j and bi with bj. So after that, you are given n and k. Count the number of such arrays. So we have a B is called good now. So we need to count the number of arrays A of length n such that AI it should be greater than equal to 0 and less than equal to 2 power k. And A should be good. So what they are trying to say is, so let's say if we have an array B is equal to let's say if we have an n is equal to 3 and k is equal to 2. So 2 in the sense 2 power 2, right? We can use 2 power 2. Can use 2 power 2. 2 power 2 in the sense less than 2 power 2, right? So less than 2 power 2. Then 0, 1, 2 and 3. So these are the four elements we can't use to construct an array of size n is equal to 3. So we need to create n is equal to 3. Let's say if we can use 2 over here, 1 over here and 3 over here. So the operations, let's say we are doing the operations right now. So we need to make each and every element of this array as 0. So the target will be like we need to construct a 0, 0, 0, right? So this is how we need to do. So let's say if we let's take two indexes. Two indexes I and I less than j says that we need to take two distinct integers. Like we can't take 2 and 2 like that. So we need to take 2 and 1 something like that or 2 and 3. So what they are trying to say is, so let's now take 2 and 1 over here. We have 2 and so the first index will be 2 and the next will be 1. So what is the value of x over here? So let's write the number in binary now. Here it is 1. So the XOR after doing the XOR what we have? We have 11. 1 1. 1 1 in the sense we have 3 in decimal representation. So right now what we need to do? We need to replace 2. We need to replace 2 with 3. 3 minus something. So we need to replace 2 with x minus 2. We need to replace 1 with x minus 1, right? So what will happen? So x here it will become 1 and here it will become 2. So there is no point in choosing this subarray, right? So we will neglect this part and we'll just try taking some other. We'll just try taking some other part. So this is all is. We'll just remove part this now. Um, hmm. So right now we are supposed to take 2 and 3. So let's take, we are going to take 2 and 3. So we are going to find the value of x. So 2 in binary representation as 1 0, 3 in binary representation as 1 1. So what is the bitwise XOR of these things? So if we have 1 over here, then we will obviously write 1. There is obviously 1. So the bitwise XOR will be 3. 3, right? So let's do the same scenario over here. We replace 2 with x minus 2. we replace 3 with x minus 3. So what is the result? X value of x is 3. 3 minus 2 is 1. So what we will do over here? 3 minus 3 is equal to 0. So we have noticed that the numbers are getting changed. So obviously the array B is equal to, change the color. Second. So color, instead of 2 we have 1 over here, and instead of 1 there is no change over here, it is 1 only, and instead of 3 what we have noticed, we have 0. So this is the like array after that operation, right? So we have noticed the change over here and over here. So after the second operation, what is our straightforward approach? We will just take 2 and 1 and 1, 1 and 1. So the bitwise XOR will be 1. So we will change x minus 1, and here also x minus 1. Obviously x also 1, right? X is also 1, 1 minus 1 and 1 minus 1. So now everything will become 0, right? So this part is also become 0 and this part is also become 0. So this is a good array. So we notice that this is obviously a good array, right? Hmm. So let's take one more example. Hmm. Hmm. Let's take one more example. Let's say if we have an array like 1, 1 and 1, right? So here we see that let's take 1 and 1. So obviously in our previous operation also we have done something related to this. So if we have this thing, we will make use of like 0 and 0 and 1 only. So we can notice that there is no operation in which we are able to make this one as 0, right? There is no pair. So if we take 0 and 1, obviously this both will get changed only. After this operation, it may be 1, 0, 1. So we can, at last we can say that this is not a good array. So this is so when we are calculating the total number of subarrays, it won't be calculated, since we can't do any kind of operation like that. Hmm. So let's try to notice what is happening right now. Hmm. So let's compare 2, 3, 1, 3. Yeah, it's 2, 1, 3. Let's say 2, 1, and 3. So after doing such operation, the array is becoming how? Let's say 1, 1, and 0. So let's keep in track about the bits. Let's say if we have 2 bits over here, bit at 2 range and bit at 1 0 range, like 2 power 0 and 2 power 1 kind of. So in 2 power 0 we have let's say for 1, 0, 1, 2, 1, 0, 3, 1, 1. So in zeros operation we have two elements initially, 2. In 2 power 1 we have 2 operations. So after this operation, what is happening over here? For this part, just notice we have only 1. We have two ones. So 2. We have 0 over here. So that we can notice that so whatever the operation in which we are doing, uh, so this operation replace bi with bi, x minus bi and bj with x minus bj. So this particular operation is trying to reduce the number of bits in even bit. Let's so this is C. So here it is 2 and it is become as 0. Like at a particular operation we can reduce 2. I mean we can reduce even number of such bits. Now let's try to examine with some other example. Mm, let's say if we have an array of, we have size 2 only. K is equal to 3 kind of 2. Let's say 1, 2, or 3, or 0. Let's take, we have 3 and let's say if we have 5 over here. Hmm. Let's say if we have 1. So 3 and 1. So obviously if we take 3 and 1 in our previous example itself we have noticed. Hmm. So let's say 3 and 1. Hmm. I think for this case it won't happen. Hmm. Let's see for 3 and let's say if we have three numbers itself. If we have notice till 8 we can use. Hmm. Till 7. So till 7 distance if we have, let's say if we have 7 over here. Let's say if we have 5 over here and we have 2 over here. So obviously the 7 is 5, 5 and 2. So we are trying to check whether it is an a correct subarray or not, and we also observe that how it is getting updated. Let's say we will just create this table over here. 2 power 0, 2 power 1 and 2 power 2. Since we are taking a 2 power less than 2 power 3. Hmm. So we'll just calculate the initial subarray. For 2 updated here, updated here, right? We have 1. For 5 this also updated and this also updated. 4 plus 1 5. For 7 all the 3 will get updated. So we have 2 over here, we have 2 over here, 2 over here, we have 2 over here. Basically we are just adding this part, like for 2 we will have 2, we will have 2. So that is, so let's try to take 5 and 2 over now for now. Let's try to take 5 and 2. We have taken 5 and we have taken 2. We are trying to find the bitwise OR. For 5 we have this, for 2 we have this. Hmm. Basically it won't do any such operation. So let's take 5 and 7. So for 5 we will have 5. For 7 we will have this. So what is the bitwise OR? We will have 1 1 1. So bitwise OR will be 7. Mhm. So 7, right? So what we will do right now here is we will just do that subtraction operation, x minus 5 and x minus 7. So x minus 5, 7 minus 2, this becomes 2 and this becomes 0. So this is the main part. We have so right now the array will be like instead of 2 instead of 2 7 5 2 and 7 5. Instead of 7 we have 0. Instead of 5 we have 2. Instead of 2 we don't updated anything. So right now we can notice that we have two twos. We have two twos only. No zeros and no zeros. No. So see, so whatever the operation in which we are doing, we can notice that we can be able to reduce that particular bit in an even way. So that's why. So let's say if we have 1 over here and we are just trying to remove from that part. Mm, let's say I just got an assumption. Mm, mm, let's say if we have one only. Uh, let's draw a good line. Mm, mm. So let's say if we are talking about only one bit. Let's say if we in our first bit we have 0 and in our second bit we have 1. Second bit in our 1 and we have 0. Let's take 1 1 1 1 and there is no particular bit at particular place. So uh, what is the XOR for this particular what is the OR for this bit? We have 1, we have 1, we have 1, we have 0, right? So let's say if we this is bi, let's say if we have a and b, this is OR. Hmm. OR in the sense we have x is the OR, right? Hmm. So what we will do, this is x minus a, and the next part will be x minus b. Hmm. So let's say if we are in our a part we have 0, in our b part we have 1, in our x part. So what will be the value of x minus 1? So x is 1, a is 0, it becomes 1. Let's say if we have 1, b is equal to 1 and x is equal to 1, x minus b is equal to 0. Let's say if we have 1 over here, x minus 1 is 1 minus 1 is equal to 0. 1 minus 0 is equal to 1. If we have 1 and 1 over here, let's say if we have 1 over here, x minus 1, this is 0, this is 0. We have 0 and 0. There is no changes, there is no changes. So, so whatever the bit in which if we are having, let's say 0 and 1, after this operation, there is a small swap only. So this operation also does the same thing. If we have 1 and 0, and this operation is getting swapped, like a is become 0 and b is equal to 1. So there is no changes we have, like there is no reduction operation we have done at this part. But see, if we have 1 and 1 over here, this is getting reduced to 0 and 0. So this is the main observation in which why we are taking odd and even parts. Let's say if I have seen the no, if we have two, we can reduce it. We have the possibility of reducing this from a even to an even. Like if we have six, in first operation we can reduce to 4, and second operation we can reduce to 2, and at the last operation we can make it as 0 as well. But what if we have this kind of thing, 1 1 1? We have three ones over here, and the first operation we can make 3 to 1, but we can't make 1 this to 0, right? So as per assumption we said that if the count of 1 is 1, we can't make only, the only possibility is just to swap. We can swap only. But if we have two ones, we can make it is 0. So this is the main table. Like we can't assume this is our main learning from this particular problem. Like if we have noticed that like these things, we can get good to go. Hope you have got these things right. Mm. Let's move ahead. Mm. Mm. So let's say if we have n is equal to 5, mm, and k is equal to 2. So in the sense we can use 2, 0, 1, 2, and 3. As I said that we have n is equal to 5, right? We will just have this part, n is equal to 1. In the first element I'm saying. This is the first element. And for n is equal to 2. And we have n is equal to 3. And n is equal, I is equal to, we can say I is equal to. Uh, let's say this is our I is equal to. These are I is equal to. I is equal to. In the first question, the second and third and fourth, like that, right? Let's say if we are, let's always add the number in binary representations. Let's add, say if we have this part to add, right? So we'll try to add 3 over here. So whenever we are adding, just try to add in binary. In for observation sake, I'm saying we have 11, 1 1 distance 3. We try to add 2 over here. We try to add 1 over here. We try to add another 3 over here. So this is the crucial thing in which we are going to take place. So at I is equal to 5, we already observed now. So whenever a particular bit, um, whenever the count of particular bit is even, then only we will be able to reduce all this to 0. So if the count is 5, then we can't obviously make to 0, right? So if we can make it to 3 and we can make it to 1, at some point at 1 we can't make to 0. If we have the count of that particular bit as 6, we can make to 4, we can make to 2, and we can make to 0. So this is how the particular bit will come into 0. So the main thing will be, if a particular bit AI is even, then obviously we are able to make that particular bit as 0. Let's come into assumption over here. So the first bit, until this part we have just added random randomly. But this part is not going to do that those things as like before. We can't randomly say we will just put 0 or put 1 or 2 or 3. Let's count the bit from right now. We have 1, we have 2, we have 3, we have 3 ones, right? So obviously if we have 3 ones and put over here 0, then the particular element will be at odd, then we can't make to 0. So it will become not a good array, right? So obviously we need to make for 1 for sure. We need to make 1 for sure. So obviously the same thing will be going to happen over here. We have 3 ones only. So this part only 1. So after this, if we try to do the operations, ultimately we can able to make the array as 0, right? Since each bit is in even number. 1, 2, and 3, 4. We have 4, we can obviously do 4 to 2 and 2 to 0 kind of, which is obviously possible. So here also it will be the same thing. We will just subtract and subtract and we'll just go to do. Let's take one more example from the above part, right? Hmm. Also we just take n is equal to 3. 3 instant 2 power 3 less than equal to 2 power 3. We can able to do until 7, right? Now let's do. So this is parts are random parts. So until I is equal to 4, I will just try to add the numbers randomly, as I said already now. So let's say if we are trying to add 5 over here, I am trying to add 0 over here. So this is things which I am trying to add randomly. I am trying to add 6 over here. I am trying to add 1 over here. Right? So let's start checking with the bit parity. So in the first at 2 power 0, we will have 1 over here and 1 over here. So obviously it is already at even number. Right now we can't add 1 over here, right? So if we had 1, then the bit parity will become odd. Then we can't make 0. So that's why we are trying to add 0 over here. Here it is odd. So ultimately we need to add one more 1 to make the number of to make the count as even. Obviously it is already 1, already even. Then we just add to it. So what we are trying to observe over here is we can't add randomly. Randomly in the sense whatever the number which we are taking over here, that is not going to affect our good subarray, good array, right? So we can add like we can add something over here also. We can add. So if we have changed over here, ultimately the last index element only just going to reflect. So we can say that we have the possibility of adding 0 or 1 till 7, right? We have the possibility till 7. So this part, no, this part, uh, right? For the same for this row also, for this row also, for for this row also, right? So obviously, what we are saying that, mm, just a second. Mm, uh, but the thing which is not applicable for this particular row. We have till 7 possibilities, we have till possibilities. So whatever the thing which you are doing, it will have only one possibilities that is going to occur over here based on the above calculations. Let's say if we have all the numbers as 7, then all particular element will be 1. So there will be four numbers which is even. Obviously we will write 0. What if there is only one at particular this bit? It is a kind of odd. Then we need to add one more bit as 1 to make this row as even, right? So this is what we will do in a continuous way, right? So hope I'm clear. Now let's see the constraints of this part. Let's see the constraints. Hmm. So see here the constraints are n is equal to 10 power 6. 10 power 6. K is equal to 10 power 6. 10 power in the sense we need 10 power 6, which is obviously very large, because we say that 2 power 64 itself, which is almost similar to 10 power 18. So this is how we can fit in our long integer itself. So what if we are going to try to like produce a number like this? Obviously we can't. We need to perform some kind of operation, right? So let's go on through a optimized approach. How the combinations are working optimized. OPTL. Optimized approach. Let's say if we have n is equal to 6. Let's say if we have n is equal to 6. We have n is equal to 6 rows, right? As previously discussed. So we will just neglect the above part only, right? We'll just do the 10 per I is equal to 6 part. So till the I is equal to 5, what we will just do, and we will take k is equal to 5. K is 5 is already it's being very big. So in the first row we have 2 power k opportunities. We have 2 power k opportunities. We have 2 power k. At I is equal to 4, we have 2 k power k opportunities. At I is equal to 5, 1, 2, 3 and 4, and this is 5, right? So we have this much of opportunities at I is equal till I is equal to 5. At I is equal to 6, there is only one possibility which is going to apt for the above. So there is only one. So we are going to find all such combinations, right? So what we'll obviously do, we'll just multiply. So the total number of possibilities will be like 2 power k star 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 1. So this is how many times? This is just a minute. This is n minus 1 times. This is 1 time. So multiplying with star 1 doesn't make any sense, right? So we'll just report this part. So we have n minus 1 times. So ultimately, what we'll just trying to do, we have 2 power k into 2 power into n minus 1, right? So we have n minus 1 2 power k. That's why we are just putting this part. So what we'll do, so 2 power k star n minus 1. So what they are mentioned at last, we need to do the modular operation after doing this part. So we need to return the answer as something 9 just good to say. Hmm. See, we need to return, since the answer may be since the number of arrays might be very large. Yes, obviously it is very right, 2 power k. Hmm. So we need to return print the modulo 9982445 3. Yeah. So we can't do the direct multiplication also, right? So to power since we have k is equal to k is also 10 power 6 5 something kind of one. Let's check that. We have 10, n is equal to 10 power 6 and k is equal to 10 power 6. Uh, so here it is also uh, 10 power 6 and n is equal to also 10 power 6. So right now we are just multiplying, right? So what it will become? We need to find the answer for 2 power 12 in our worst case modulo. So obviously trying to multiply 2 into 2 into 2 into 2 power 10 times 2 power 12. No, no, 2, not 2. This is 10 power 12 into 10 power 12 times, which is obviously very big, right? We can't do at max we can do 10 power 7 or 10 power 8 only, right? So what we are trying to do here is we are going up to take binary exponential. So this is the key problem. So binary exponential is an most popular algorithm, exponential. Uh, so what it does is we'll just write the above part in a binary exponential. Binary exponential. Let's say if we are going to take 2 power 7, we no need to multiply 2 into 2 into till 7 times. We just try to iterate till 3 part only. We just make 3 iterations only and we will just calculate that part. So 2 power 7 like that. So so for this sake we can't like we can refer the code of from GFG. Mm, let's so we have right now. So what does it says? We just do binary exponential on 2 power k star n minus 1 mod that 998, that part. So this is how the answer became. So obviously just doing this part is very easy in coding, but the logic in which we are building, so we have built such a huge logic now right now. So this is also the main keynote of this particular problem. If we have one and one over here, then only it will become 0 and 0. So this is the main observation in which we are taking. I hope the video is too length, but uh, the solution code will be very short. But the thought process and the observation in which you are going to make at this particular problem is very huge, and it can be used in our future problems as well. Like bit manipulation is the only thing in which you will make many such observation in binaries, right? So thanks for watching.